You step outside into the night, and the air feels cooler than you expect. The world around you softens. Sounds grow distant. The sky stretches wide above your head, an enormous dark ocean scattered with quiet points of light. For a moment, you simply breathe. The stars do not rush you. They do not demand understanding. They glow with steady patience, as they have for billions of years. And as you look at them, something subtle begins to shift inside you. They no longer feel like decoration. They feel like questions. Each star is a sun. This is the first whisper. Long ago, humans believed those lights were small, fixed to a crystal sphere. But now you know better. You know that nearly every star you see is a massive, burning sphere of hydrogen and helium, fusing atoms together deep in its core. You know our own sun is just one among hundreds of billions in our galaxy alone. And if our sun has planets circling it, Earth, Mars, Jupiter, then perhaps other stars do too. You let that thought settle gently. A star is not solitary. It forms from a collapsing cloud of gas and dust. As gravity pulls material inward, the cloud begins to spin. And when it spins, it flattens into a disk, like a slowly turning pancake of light and dust. At the center, a star ignites. Around it, leftover material continues to swirl. From that swirling disk, tiny grains of dust begin to collide. They stick. They gather. Over time, millions of years, they grow into rocks, then mountains, then worlds. Planets are not rare accidents. They are natural consequences. You imagine those disks forming everywhere. Around bright blue stars. Around small red ones. Around stars older than our sun and stars just now being born. Quietly, consistently, the universe makes planets. For most of human history, we could only wonder. The planets around other stars, exoplanets, were invisible to us. Too small. Too faint. Lost in the glare of their suns. It seemed possible they existed, but we had no proof. The idea hovered like a dream just beyond reach. Then, in 1992, astronomers detected something remarkable. Not around a sun-like star, but around a pulsar, the dense, spinning remnant of a dead star. Tiny variations in the pulsar's timing revealed the gravitational pull of orbiting planets. It was the first confirmed discovery of worlds beyond our solar system. You pause on that moment. For the first time, the question shifted. It was no longer, do planets exist elsewhere? It became, how many are there? And the answer, it turns out, is astonishing. Over the past decades, telescopes have watched stars with exquisite precision. They have measured tiny dips in brightness when a planet passes in front of its star. They have recorded subtle wobbles in a star's motion caused by the gravitational tug of orbiting worlds. Again and again, the same conclusion emerges. Planets are everywhere. In our galaxy alone, the Milky Way, there may be hundreds of billions of them. Some are enormous gas giants orbiting scorchingly close to their stars. Some are rocky worlds slightly larger than Earth. Some drift in multi-planet systems more crowded than our own. Some circle small, cool red dwarfs that glow faintly in the dark. You let the scale sink in slowly. Hundreds of billions. The night sky no longer feels empty. It feels populated. Each star you see may host its own family of worlds, some barren, some violent, some frozen, some warm. The universe is not a lonely lighthouse in an empty sea. It is an archipelago of systems, each with its own silent architecture. And yet, even with this abundance, something tender remains unresolved. You think of Earth. of oceans reflecting sunlight, of forests breathing, of life stirring in soil and sea. You think of the way your own body depends on air and water and warmth. You think of the delicate balance that allows you to stand here at all. If planets are common, that does not automatically mean life is common. But it changes the mood of the question. Instead of asking whether the universe has the capacity for life, you begin asking whether it has the opportunity. You picture a distant star. Around it, a small rocky planet circles at just the right distance. Not too close, where heat would strip its atmosphere away. Not too far, where water would freeze into permanent ice. Somewhere in between. On its surface, perhaps clouds gather. Perhaps rain falls. Perhaps chemistry stirs quietly in shallow pools. Or perhaps not. The beauty of this moment is that you do not yet know. The night sky above you becomes less of a ceiling and more of a doorway. Each star is a threshold. Behind it may lie barren rock or swirling gas. Or something gentler. Something breathing. You feel how vast the timescales are. Stars live for billions of years. Planets cool slowly. Chemistry unfolds in patient sequences. Life on Earth began relatively quickly once conditions allowed it, within a few 100 million years after the planet formed. That fact alone feels significant. It suggests that when the conditions are right, life may not hesitate. But conditions matter. Temperature matters. Atmospheres matter. The steady flow of energy from a star matters. The presence of certain elements, carbon, hydrogen, oxygen, nitrogen, matters. You do not rush ahead to conclusions. You simply notice that the ingredients are not exotic. They are common in the cosmos. Hydrogen is the most abundant element in the universe. Carbon forms in stars and spreads through space when they die. Oxygen is forged in stellar cores and released in brilliant supernovae. The atoms in your body were once inside ancient stars. This realization folds the sky inward. It makes the distance feel smaller. You are not separate from the universe you were questioning. You are made of it. And so the whisper grows softer, but clearer. If stars routinely form planets, if planets often contain the raw materials for chemistry, if life arose on Earth relatively early, then perhaps the universe is not silent because it is empty. Perhaps it is silent because it is vast. You stand beneath the night sky a little longer. The stars flicker, not because they are unstable, but because Earth's atmosphere gently shifts the light as it travels toward you. Even that flicker is a reminder: light carries information. It travels across space, bearing stories from distant systems. You do not yet know how to read those stories. Not fully. Not yet. But others are learning. They are learning how to look at starlight and detect the faint shadow of a passing planet. They are learning how to measure the smallest wobble and infer the presence of an unseen world. They are learning to listen to the subtle language of gravity and light. And as you gaze upward, you feel the question settle into your chest like a quiet ember. If planets are everywhere, could life be too? The night does not answer. It does not confirm or deny. It simply remains vast, patient, and full of possibility. And somewhere beyond your sight, around a distant star, unseen worlds continue to circle in the dark, waiting to be found. You remain beneath the night sky, but now your imagination begins to move. The stars above you are no longer distant decorations. They are destinations. And though your body stands still on Earth, your mind drifts outward, crossing the quiet gulf between suns. You pass beyond the familiar orbit of Neptune. beyond the scattered icy bodies of the Kuiper belt. Beyond the faint boundary where the sun's influence slowly gives way to interstellar space. The warmth of our star fades behind you, becoming just another point of light among many. And then you begin to understand something profound. For centuries, humans searched for planets around other stars and found nothing. The reason was simple and humbling: planets are small, and stars are blindingly bright. Trying to see an exoplanet directly is like trying to spot a firefly beside a lighthouse from thousands of miles away. So astronomers learned to look differently. Instead of seeing the planets themselves, they watched the stars. Imagine a star as a steady lamp glowing in darkness. If a planet passes in front of it, an event called a transit, the star's light dims ever so slightly. Not dramatically. Not enough for your eyes to notice. But sensitive telescopes can measure that tiny dip, sometimes less than 1% of the star's brightness. It is a soft blink. A rhythm. And if that blink repeats at regular intervals every few days, every few weeks, every year, it reveals an orbiting world. You picture this gentle shadow crossing a distant sun. Again and again. A cosmic heartbeat. This method, known as the transit method, has revealed thousands of exoplanets. Space telescopes like Kepler have stared at patches of sky for years, patiently measuring the brightness of over 100,000 stars. From those quiet observations, entire planetary systems have emerged. But there is another way to listen. Gravity leaves fingerprints too. A planet does not simply circle a star. Both the star and the planet orbit a shared center of mass. The planet's gravity tugs on its star, causing it to wobble ever so slightly. This wobble shifts the star's light toward red and blue as it moves away from and toward Earth. This is called the radial velocity method. You cannot see the wobble directly, but you can measure the subtle stretching and compressing of light waves. It is as if the star is whispering its own motion. Light becomes a messenger. Through these two methods, transits and wobbles, the invisible becomes known. The unseen becomes measurable. And slowly, steadily, the census of exoplanets grows. You begin to meet them. The first surprise is how strange they are. Some are called hot Jupiters. Massive gas giants like Jupiter, but orbiting incredibly close to their stars, sometimes completing an orbit in just a few days. Their atmospheres are heated to thousands of degrees. Winds scream across their skies. Clouds may be made of vaporized metals. They are nothing like the orderly planets of our solar system. Then there are super-Earths. Rocky worlds larger than Earth but smaller than Neptune. We have none like them here, yet they seem to be common elsewhere. Some may have thick atmospheres. Some may be covered in deep global oceans. Some may be dense, iron-rich worlds with crushing gravity. You imagine standing on such a planet. Your weight doubled. The sky tinted by unfamiliar gases. The sun above glowing redder or whiter than our own. There are many Neptunes, two planets wrapped in thick layers of hydrogen and helium, perhaps hiding rocky cores deep beneath. There are planets orbiting binary stars, where two suns rise and set in a shared sky. There are rogue planets drifting alone through space, unbound from any star, carrying internal heat like a hidden ember. The diversity astonishes you. Our solar system once felt like a template. Now it feels like one variation among countless designs. And yet, amid this strangeness, you search for something familiar. You look for rocky worlds. Planets roughly the size of Earth. Worlds that might have solid surfaces where chemistry can settle and linger. You learn that many stars host such planets. Some systems contain multiple rocky worlds packed tightly together, orbiting small, cool red dwarf stars. Red dwarfs are the most common stars in the galaxy. Smaller and dimmer than our Sun, they burn slowly and steadily for trillions of years. Around them, planets must orbit closely to receive warmth. That closeness raises questions about stellar flares, about radiation, but it also opens possibility. If red dwarfs are abundant, and rocky planets commonly circle them, then the number of potentially tempered worlds may be enormous. You let that possibility breathe. Thousands of exoplanets have now been confirmed. Thousands more candidates await verification. Statistical studies suggest that, on average, most stars host at least one planet. Many host several. The Milky Way may contain tens of billions of rocky planets within their star's habitable zones, regions where temperatures could allow liquid water. You do not rush to conclusions. But you notice the pattern. Planets are not rare. Rocky planets are not rare. Planets in temperate orbits are not rare. The night sky grows more crowded in your imagination. Each star becomes a system. Each system becomes a story. Some stories are violent, worlds scorched and stripped. Some are frozen and silent. Some are shrouded in thick atmospheres. And among them, perhaps, are worlds where chemistry unfolds gently. You think of gravity again, that invisible sculptor. It gathers dust into planets. It binds systems together. It creates the dance that astronomers detect from across light years. Gravity is quiet, but persistent. It shapes destinies over millions of years. And light carries the record. Every photon that reaches Earth from a distant star has traveled through space, untouched, for years or centuries. If a planet crosses that star, the light dims. If a star wobbles, its light shifts. These tiny changes, measured with care, reveal entire worlds. You feel a sense of humility in this. We have not traveled to these planets. We have not touched them. Yet through careful observation, we know they are there. It is like hearing footsteps in another room. You cannot see who walks there, but you know the floorboards creak. The universe is not silent. It leaves traces. As you drift in thought among these exoplanets, one idea begins to glow softly at the center of your mind. Among all these strange and varied worlds, which ones are gentle enough for life? Which orbits provide steady warmth? Which atmospheres protect fragile chemistry? Which surfaces hold oceans, or lakes, or shallow tidal pools where molecules might gather? The question narrows, becomes more specific. Not just, are there planets? But, are there planets where liquid water can exist? You feel yourself approaching the delicate boundary, the region around a star where temperature, distance, and energy balance in just the right way. A narrow band. A fragile ring. A zone where warmth becomes possibility. You move closer now, not to a specific planet, but to an idea. Around every star, there exists a region where warmth gathers in a careful balance. Not blazing and destructive. Not distant and frozen. But gentle. Measured. Enough. Astronomers call it the habitable zone. You might have heard it described as the Goldilocks zone, not too hot, not too cold, but just right. Yet the phrase, simple as it sounds, carries immense weight. It represents a narrow ribbon of possibility wrapped around a star. You imagine drawing a circle around a distant sun. Too close, and water boils into vapor, escaping into space. Too far, and water freezes solid, locked in ice. But between those extremes lies a range of distances where liquid water can persist on a planet's surface. Liquid water. It sounds ordinary to you because you are surrounded by it. Oceans stretch across your world. Rain falls. Rivers carve valleys. But in the vast cold of space, liquid water is rare. It requires the right temperature and the right pressure. It requires an atmosphere capable of holding warmth. Water is remarkable. It dissolves substances. It allows molecules to move, collide, and react. It becomes a stage where chemistry can grow complex. On Earth, every known form of life depends on it. So when scientists speak of habitability, they begin with water. You imagine standing on a rocky planet orbiting within this zone. The star above shines steadily. The surface temperature allows oceans to ripple instead of freeze. Clouds gather and drift. Rain falls in slow rhythms. It feels possible. But warmth alone does not guarantee gentleness. A planet too close to its star may enter a runaway greenhouse state. You think of Venus, once perhaps similar to Earth, now shrouded in thick carbon dioxide clouds, its surface hot enough to melt lead. Even if it lies near the inner edge of the Sun's habitable zone, its atmosphere traps heat relentlessly. Distance matters. But atmosphere matters too. You begin to see that the habitable zone is not a fixed ring etched in stone. It depends on the brightness of the star. A massive, luminous star casts its zone farther outward. A small red dwarf draws it inward, close to its faint warmth. Stars change over time. As they age, they brighten or dim. The habitable zone shifts. Planets that once lay within it may drift beyond its boundaries as stellar output evolves. The concept is dynamic, alive. And then there is the question of stability. Life, as far as you know, thrives on steady energy. Not violent flares. Not dramatic temperature swings. The sun provides relatively stable light. Its fluctuations are small enough that Earth's climate remains balanced over long spans. But many red dwarf stars are active. They flare frequently, releasing bursts of radiation. A planet orbiting close enough to stay warm might also endure intense stellar storms. Such flares could strip away atmospheres or bathe surfaces in harsh ultraviolet light. You begin to understand that habitability is a symphony of factors. Distance, stellar type, atmospheric composition, magnetic fields, planetary mass. A planet must be large enough to hold an atmosphere. Too small, and gases escape into space. Mars, once warmer and wetter, gradually lost much of its atmosphere due to weak gravity and solar wind. Gravity becomes a quiet guardian. You imagine a rocky world slightly larger than Earth, a super-Earth, with enough mass to retain thick air. Its atmosphere contains carbon dioxide, perhaps nitrogen, perhaps water vapor. Greenhouse gases trap some heat, preventing oceans from freezing. Clouds reflect excess light, preventing overheating. It is a balancing act. Even plate tectonics may play a role. On Earth, the slow movement of continents recycles carbon between the atmosphere and the crust. Volcanoes release carbon dioxide. Weathering processes draw it down. This long-term carbon cycle stabilizes climate over millions of years. Without such regulation, a planet's temperature might swing too far in either direction. You begin to feel the fragility of it all. The habitable zone is not a guarantee of life. It is a doorway, a threshold. And yet, the numbers remain astonishing. Astronomers estimate that billions of stars in our galaxy may host rocky planets within their habitable zones. Billions of potential shores where water could lap gently against stone. You picture them, countless worlds circling in quiet orbits, warmed by their suns. But you do not rush ahead to imagine forests or creatures. You stay with the physics. Energy flows from a star in the form of light. A planet absorbs some of that energy and radiates heat back into space. When incoming and outgoing energy balance, temperature stabilizes. If incoming energy overwhelms outgoing heat, the planet warms. If too much heat escapes, it cools. Climate is an equation written in light and atmosphere. You feel how delicate that equation is. A slight increase in greenhouse gases can tip the balance. A slight decrease can plunge a world into ice. And so you ask yourself quietly, if warmth is present, if liquid water can exist, is that enough? On early Earth, life emerged relatively quickly once oceans formed. Microbial life appeared perhaps within a few 100 million years after the planet cooled. That suggests that given water and energy, chemistry may naturally progress toward biology. But the origin of life remains one of science's deepest mysteries. You do not yet know exactly how simple molecules assembled into self-replicating systems. You do not know how common that transition is. You only know that warmth creates opportunity. You feel a sense of reverence for this narrow band around each star. It is not flashy. It is not dramatic. It is simply a region where water can remain liquid long enough for chemistry to explore itself. In the vastness of space, that seems miraculous. And yet, something inside you senses that temperature alone is not the full story. A planet may lie in the habitable zone and still lack the right ingredients. It may have warmth but no atmosphere. It may have oceans but no carbon. It may have energy but no stable chemistry. You begin to understand that habitability is layered. First, the right distance. Then, the right atmosphere. Then, the right chemistry. And chemistry, that is where the story deepens. Because even if a planet rests comfortably within its star's gentle embrace, you still must ask what fills its air. What molecules swirl in its skies? What gases gather and linger? It is not enough for a world to be warm. You must learn to read its breath. You lean closer now, not toward a star, not toward a planet, but toward something smaller. Far smaller. You shrink in your imagination until mountains become grains, and grains become clusters of atoms. You descend into the invisible world where matter rearranges itself endlessly, quietly, without spectacle. Here, everything is motion. Atoms drift, collide, separate, and rejoin. They are not solid beads but structured clouds of probability, tiny nuclei surrounded by restless electrons. And when conditions are right, these atoms join together, sharing electrons like hands clasped in a circle. These joined atoms are molecules. Molecules are the words of planetary atmospheres. They are the letters that spell out a world story. You picture a distant rocky planet resting within its star's habitable zone. Its surface may hold oceans. Its skies may hold clouds. But what truly defines it, what gives it personality, is its air. Air is not emptiness. It is a blend of molecules suspended in motion. On Earth, the dominant molecule is nitrogen, quiet, stable, making up most of the atmosphere. Oxygen follows, reactive and energetic. Then there is carbon dioxide, methane, water vapor, each present in smaller amounts, yet each powerful in its influence. Now imagine reading that atmosphere from across light years. You cannot travel there. You cannot sample the air directly. But if the planet passes in front of its star, some of the starlight filters through its atmosphere before reaching you. Certain wavelengths of light are absorbed by specific molecules. Each molecule removes its own narrow bands of color from the spectrum. It is as if each gas leaves a fingerprint in light. You begin to understand why molecules matter so deeply. They are not just ingredients. They are signatures. Oxygen absorbs light at particular wavelengths. So does methane. So does water vapor. By examining the missing pieces of starlight, astronomers can infer which molecules are present. This is spectroscopy, the art of decoding light. But the story grows more subtle. Certain molecules are chemically reactive. They do not like to coexist for long without continuous replenishment. Oxygen, for example, readily reacts with rocks and gases. Methane breaks apart under ultraviolet light. If you detect large amounts of both oxygen and methane in the same atmosphere, something curious emerges. They should destroy each other. Unless something is producing them continuously. On Earth, life performs that task. Plants and microbes release oxygen through photosynthesis. Other microbes generate methane in oxygen-poor environments. The coexistence of these gases reflects a planet in chemical imbalance, a state known as disequilibrium. You imagine atmosphere as a musical chord. In a purely chemical world without life, reactions tend toward equilibrium, a quiet resting note. But life introduces tension. It pulls systems away from their natural resting state, sustaining combinations that would otherwise fade. Disequilibrium becomes a potential clue. Yet you move slowly here. Gently. Because chemistry alone can sometimes mimic life. Volcanoes can release methane. Ultraviolet light can split water vapor, allowing hydrogen to escape and leaving oxygen behind. Planetary processes can produce surprising mixtures. You do not jump to conclusions. Instead, you listen. The language of molecules is subtle. It requires context. You imagine examining a distant planet's atmosphere and detecting water vapor. That suggests moisture, perhaps clouds. You detect carbon dioxide, common and expected. Then you notice oxygen, not in trace amounts, but abundant. You pause. Oxygen is reactive. It wants to combine with other elements. For it to remain abundant, something must constantly replenish it. On Earth, that something is life. But is Earth unique? Or is oxygen a common byproduct on other worlds under certain conditions? This is why the search for life does not rely on a single molecule. It seeks patterns, relationships, context. Carbon chemistry plays a central role. Carbon is versatile. It forms long chains, rings, complex structures. It binds with hydrogen, oxygen, nitrogen. It builds amino acids, sugars, lipids. When you consider life, you consider carbon-based molecules in liquid water, powered by steady energy. You imagine these molecules swirling in a shallow pool on a young planet. Sunlight warms the surface. Water allows molecules to drift and collide. Reactions occur. Some structures form and fall apart. Others persist longer. Chemistry becomes experimentation. Over vast stretches of time, certain molecular arrangements may begin to replicate, to copy themselves imperfectly. Selection may begin not conscious, not deliberate, but statistical. Structures that persist become more common. From simple molecules to complex networks. Yet from afar, you cannot see that process unfolding. You can only observe the atmospheric aftermath. Life breathes. Life metabolizes. Life exchanges gases with its environment. The air becomes an archive of biology. You realize that planetary atmospheres are not static blankets. They are dynamic systems shaped by surface processes, volcanic activity, stellar radiation, and perhaps, just perhaps, living organisms. The trick is to disentangle these influences. You imagine a spectrum of starlight stretched out before you like a rainbow. Dark lines appear where molecules have absorbed specific wavelengths. Each line corresponds to a transition in molecular energy levels, electrons jumping between states, bonds vibrating in response to light. It is physics at its most delicate. From across dozens of light years, humanity attempts to read these faint imprints. It is astonishing. You feel a quiet awe at the precision required. Tiny dips in brightness. Subtle spectral signatures. Signals buried in noise. Yet slowly, patterns emerge. Water vapor has been detected in exoplanet atmospheres. So has carbon dioxide. Methane too, in some cases. Each detection refines our understanding of planetary diversity. You feel the narrative expanding. Instead of asking whether a planet exists, you now ask what fills its skies. Instead of counting worlds, you begin characterizing them. Some atmospheres are thick and hydrogen-rich. Some are thin and dominated by heavier gases. Some show hazes and clouds that mute spectral signals. Clouds complicate the story. They scatter light. They hide deeper layers of atmosphere. They blur molecular fingerprints. The universe does not make this easy. But that difficulty only deepens the significance of each confirmed detection. You begin to see exoplanet atmospheres as conversations. Light from a star speaks. The atmosphere replies by absorbing certain words. And astronomers, listening carefully, piece together the dialogue. If oxygen speaks loudly, what does it mean? If methane joins it, what story unfolds? If both appear together in large amounts, does the chord suggest life? You do not yet know. But you feel that the answer will not lie in a single molecule. It will lie in combinations. In context. In chemical relationships sustained against expectation. The search becomes less about spotting a forest from afar and more about smelling the faint scent of growth in the wind. You stand again beneath your own sky, breathing air rich with oxygen. Your body participates in this chemical dance. Every inhale and exhale shifts molecules between you and the atmosphere. You are part of Earth's disequilibrium. And somewhere beyond this world, other atmospheres swirl. Some may be chemically quiet, resting in equilibrium, lifeless and stable. Others may hum with imbalance, whispering of processes beneath their clouds. To hear those whispers clearly, you must learn more about one molecule in particular, the restless gas that fills your lungs and rarely lingers without life's constant renewal. You must understand oxygen. You inhale slowly. Without thinking, without effort, oxygen enters your lungs. It passes into your blood, binds to iron and hemoglobin, and travels quietly through your body. In each cell, it participates in a careful exchange, helping release energy from the food you eat. Every movement you make, every thought you think, depends on this invisible partner. Oxygen feels ordinary to you. But in the universe, it is anything but. You imagine drifting back beyond Earth, looking at your planet from a distance. Its atmosphere glows faintly blue. If a distant civilization examined Earth's spectrum, they would see strong signatures of molecular oxygen O2 absorbing specific wavelengths of light. They would know something unusual is happening here. Because oxygen is restless. It does not like to remain free for long. It eagerly reacts with other elements. It binds with iron to form rust. It combines with carbon to form carbon dioxide. It participates in combustion, corrosion, metabolism. In a purely chemical world, oxygen tends to disappear into compounds. It becomes locked into rocks or dissolved in oceans. For large amounts of free oxygen to persist in an atmosphere, something must continuously replenish it. On Earth, that something is life. More specifically, photosynthesis. You picture a leaf resting in sunlight. Within its cells, tiny structures called chloroplasts capture photons, packets of light energy. That energy splits water molecules into hydrogen and oxygen. The hydrogen helps build sugars. The oxygen is released into the air as a byproduct. A quiet alchemy of light and leaf. This process, repeated trillions of times across forests and oceans, slowly transformed Earth's atmosphere. Early in our planet's history, oxygen was scarce. Microbial life thrived without it. But around 2.4 billion years ago, photosynthetic microbes began releasing oxygen in large quantities. This event, the Great Oxidation Event, reshaped the planet. Oxygen accumulated in the atmosphere. It reacted with surface rocks. It altered climate. It paved the way for complex, oxygen-breathing life. You feel the weight of that transformation. The oxygen you breathe is a legacy of ancient microbes. Now imagine detecting oxygen in the atmosphere of a distant exoplanet. It would be tempting to celebrate immediately. Oxygen means life, you might think. Something is breathing there. Something is splitting water under alien sunlight. But you move slowly. Because nature can surprise you. There are ways to produce oxygen without life. If a planet lies very close to its star, intense ultraviolet radiation can split water vapor in the upper atmosphere into hydrogen and oxygen. The lightweight hydrogen escapes into space, leaving oxygen behind. Over time, this process can accumulate significant amounts of oxygen even in the absence of biology. Similarly, carbon dioxide can be broken apart by ultraviolet light under certain conditions, releasing oxygen atoms that may combine into O2. These processes are abiotic, non-living. You begin to see the challenge clearly. Oxygen alone is not enough. It is a powerful clue, but not definitive proof. Context matters. You imagine two distant planets. On one, oxygen appears alongside large amounts of water vapor, moderate carbon dioxide, and methane. The star is stable. The planet's temperature allows liquid water. The chemical mixture appears out of equilibrium. On the other, oxygen dominates an atmosphere stripped of hydrogen. Ozone can serve as an indirect indicator of oxygen. Yet again, the presence of ozone must be interpreted carefully. It reflects atmospheric chemistry, stellar radiation, and planetary conditions. The search becomes layered. Oxygen plus methane is especially intriguing. These gases react with each other. In Earth's atmosphere, methane persists only because life continually produces it through microbes in wetlands, through digestion in animals, through decomposition. If you detect both oxygen and methane in substantial amounts on a distant planet, the coexistence suggests continuous replenishment. A dynamic system. A breathing world. You imagine such a detection. Light from a distant star filters through a planet's atmosphere during transit. Sensitive instruments measure faint absorption lines corresponding to oxygen and methane. Data accumulates over months, then years. Statistical analyses confirm the signals. What would you feel? Excitement, certainly. But also caution. You would ask, could volcanic processes produce methane at this rate? Could photochemical reactions mimic this mixture? Is the star's radiation influencing the chemistry in unexpected ways? Science does not leap. It steps. You find comfort in that patience. Oxygen is powerful not because it guarantees life, but because it invites deeper inquiry. It narrows the possibilities. It focuses attention. You return to your own breath. Each inhale draws in oxygen produced by plants and algae. Each exhale releases carbon dioxide, which plants will use again. A cycle. A partnership between atmosphere and biosphere. Life reshapes air. This idea feels profound. Atmospheres are not passive blankets. They are active records of surface processes. They evolve. They respond. They reflect what happens below. If a planet harbors life, its atmosphere may bear subtle marks of that presence. You imagine standing on an alien shoreline beneath a sky rich with oxygen. The air smells unfamiliar, perhaps sharp. Waves roll in. Microbial mats line the coast. Or perhaps forests of strange photosynthetic organisms stretch toward a different colored sun. You let the image soften. Because you do not yet know. You only know that oxygen, though reactive and restless, can accumulate under the right circumstances. And those circumstances may involve biology or may involve intense stellar radiation and atmospheric escape. The distinction is delicate. This is why scientists seek multiple biosignatures. A single molecule is a hint. A combination, sustained against expectation, is stronger. Oxygen teaches you humility. It reminds you that even something so intimately tied to your existence must be interpreted carefully in cosmic contexts. You feel the scale of the challenge. From dozens of light years away, you attempt to read the breath of another world. To determine whether its atmosphere is shaped by geology alone, or by something more intricate. And as you rest with that thought, another molecule drifts into your awareness, simpler, lighter, and equally intriguing. Methane. Fragile in sunlight. Short-lived in oxygen. And perhaps, in its imbalance, just as revealing as breath itself. You turn your attention now to a smaller molecule. Simpler than oxygen. Lighter. Quieter in structure. Methane. One carbon atom holding hands with 4 hydrogen atoms, CH4. A small tetrahedron drifting through air, nearly invisible, easily broken by sunlight. On Earth, methane does not linger for long. Ultraviolet radiation and reactive oxygen molecules tear it apart within about a decade. And yet, it persists. It persists because something keeps making it. You imagine wetlands at dusk. Beneath the surface of mud and water, microbes thrive without oxygen. These organisms, called methanogens, metabolize simple compounds and release methane as a byproduct. In the digestive systems of animals, similar microbes do the same. In thawing permafrost, in rice paddies, in ocean sediments, methane rises quietly into the sky. Life breathes it out in hidden corners. But life is not the only source. Volcanoes can release methane. So can chemical reactions between water and certain rocks deep within a planet's crust, a process called serpentinization. Even impacts from comets may deliver methane-rich materials. You move gently here, aware that methane is ambiguous. If you detect methane in a distant atmosphere, you cannot immediately declare biology. You must ask, how much methane? In what context? Accompanied by what other gases? Methane alone is a whisper. But methane with oxygen is something more. You remember that oxygen is reactive. It eagerly oxidizes methane, converting it into carbon dioxide and water. In an atmosphere with abundant oxygen, methane should vanish quickly unless it is constantly replenished. If both gases coexist in substantial amounts, something must be maintaining the imbalance. This is where the concept of disequilibrium enters. In chemistry, systems tend toward equilibrium, a state where reactions balance out and no net change occurs. It is a kind of stillness, a resting point. But life resists that stillness. Life feeds on gradients, on differences in concentration, in energy, in chemical potential. It maintains imbalances. It pulls molecules out of equilibrium and keeps them there through constant metabolism. You imagine equilibrium as a calm lake at dawn, still, flat, undisturbed. Disequilibrium is a flowing river, dynamic, moving, shaped by ongoing input. Earth's atmosphere is a river. Oxygen and methane coexist not because chemistry prefers it, but because biology sustains it. Photosynthetic organisms produce oxygen. Methanogenic microbes produce methane. The two gases react, yet life replenishes both. This persistent imbalance is a planetary signature. You begin to see why scientists are so interested in pairs of gases that should not comfortably coexist. If you detect methane on a distant planet with no oxygen present, it might be geological. If you detect oxygen alone, it might be photochemical. But if you detect both in high concentrations and perhaps additional reducing gases like nitrous oxide, the case strengthens. It becomes harder to explain without invoking ongoing processes. And life is an ongoing process. You imagine observing a rocky exoplanet orbiting within its habitable zone. Spectroscopy reveals absorption features corresponding to methane. Further analysis suggests the presence of oxygen as well. The star is relatively stable. The planet's temperature allows liquid water. You would feel cautious excitement. But again, you would ask, could non-biological mechanisms sustain this mixture? Some researchers model exotic scenarios. For example, if a planet has an ocean that is losing hydrogen to space, oxygen could accumulate abiotically. If volcanic activity is intense, methane might be continuously released. If stellar radiation drives unusual photochemistry, surprising combinations could arise. The universe is inventive. And so the search for disequilibrium becomes quantitative. Scientists estimate production rates. They simulate atmospheric chemistry. They model planetary environments under various conditions. It is not enough to see imbalance. You must understand whether it is sustainable without life. You appreciate the rigor. Because the claim that we are not alone would be extraordinary. It must rest on extraordinary evidence. Methane also plays a role in climate. It is a potent greenhouse gas, trapping heat effectively. On early Earth, when the sun was dimmer, methane may have helped keep the planet warm enough for liquid water. On a distant exoplanet, methane could similarly influence temperature. Its presence might not only signal chemistry but also shape habitability. You begin to see atmospheres as living equations. Each molecule contributes to radiative balance, chemical reactions, and spectral fingerprints. Nothing exists in isolation. Methane's simplicity makes it chemically reactive. Sunlight breaks it apart. Oxygen oxidizes it. Its lifetime in an oxygen-rich atmosphere is short. That short lifetime is precisely what makes it valuable as a biosignature candidate. A transient gas requires replenishment. You think again of your own world. If all life on Earth suddenly vanished, oxygen levels would gradually decline as it reacted with surface materials. Methane would disappear even faster. the atmosphere would drift toward a quieter equilibrium dominated by nitrogen and carbon dioxide. Life keeps Earth's atmosphere out of balance. You imagine standing on a distant world where methane drifts through alien air. Perhaps there are microbial mats beneath shallow seas, releasing methane bubbles. Perhaps there are ecosystems you cannot yet conceive. Or perhaps the methane rises from deep volcanic vents, entirely geological. The distinction is subtle. You feel a growing appreciation for complexity. The search for life is not a hunt for a single molecule but a search for patterns that resist simple explanation. Methane teaches you that fragility can be revealing. A gas easily destroyed becomes meaningful when it persists. Short-lived substances point toward ongoing processes. And disequilibrium, that sustained tension between opposing chemical forces, may be one of the clearest signatures of life. You let that idea settle. Imbalance as evidence. Restlessness as revelation. The universe tends toward stillness. Life tends toward activity. If you can measure that activity from afar, through the faint absorption of starlight, you may glimpse biology across the void. But to detect methane, oxygen, or any gas at all, you must first see through the haze of clouds and vapor that often shroud a planet's surface. You must understand water not only as liquid, but as vapor drifting through alien skies. Because before you can interpret a world's chemistry, you must learn how to read its clouds. You lift your gaze again, this time not toward the surface of a planet, but into its sky. Atmosphere is not only chemistry, it is motion. It is circulation, evaporation, condensation. It is water rising invisibly as vapor, then gathering itself into clouds. Water changes form easily. Ice becomes liquid. Liquid becomes vapor. Vapor cools and returns as rain. On Earth, this cycle shapes climate, sculpts landscapes, and sustains life. But from far away across light years, you cannot see rain falling. You cannot watch rivers winding through valleys. You must search instead for water's subtler presence. Water vapor. When a planet passes in front of its star, a thin veil of its atmosphere filters starlight. Molecules within that veil absorb specific wavelengths. Water vapor has its own spectral fingerprints, dark bands where light is quietly removed. Sensitive instruments can detect those missing wavelengths. You imagine astronomers examining a spectrum and noticing those faint signatures. The pattern corresponds to H2O. Not liquid water directly, but vapor in the air. That alone is significant. Water vapor suggests evaporation. It suggests temperature conditions where water can exist as liquid somewhere on the planet, at least temporarily. It hints at cycles. But water is complex. Too much water vapor can create a runaway greenhouse effect. You think again of Venus. As the planet warmed, more water evaporated. Water vapor, being a greenhouse gas, trapped additional heat. More heat caused more evaporation. Eventually, oceans may have boiled away entirely. What remains today is a dense, hot atmosphere and only traces of water. So when you detect water vapor on a distant planet, you must ask, is it part of a balanced cycle or a sign of extreme heating? Context returns again as your guide. Clouds complicate the picture. Clouds are beautiful from the ground, soft, shifting sculptures of condensed droplets or ice crystals. But from a distance, clouds are masks. They reflect light. They obscure deeper layers of atmosphere. They blur spectral features. A thick cloud deck can hide the surface entirely. You imagine a distant ocean world, covered in global seas. Sunlight warms the water. Evaporation lifts moisture into the sky. Thick clouds form and drift, reflecting starlight back into space. Beneath them, oceans stretch unbroken to the horizon. From far away, the spectrum might show only hints of water vapor and muted chemical lines, softened by cloud scattering. You feel the challenge. Clouds both protect and conceal. They can stabilize climate by reflecting excess radiation. They can cool a planet. But they can also prevent you from clearly reading atmospheric composition. Some exoplanets appear shrouded in hazes, tiny particles suspended high in the atmosphere. These hazes scatter light in complex ways, flattening spectral features and making it harder to detect individual molecules. The universe does not offer its secrets easily. Yet water remains central. Life on Earth emerged in water. It relies on water as a solvent, a medium in which molecules dissolve and interact. Water allows chemical reactions to proceed efficiently. It stabilizes temperature. It transports nutrients. Where you find persistent liquid water, you find potential. You imagine standing on a distant shoreline under an alien sun. The sky above holds unfamiliar constellations. Waves lap against dark sand. Clouds gather and disperse. In shallow tidal pools, molecules drift and collide. Even if no life exists there, the stage is set. You recall that within our own solar system, water appears in many forms. Mars holds ice at its poles. Europa and Enceladus hide subsurface oceans beneath icy crusts. Titan hosts lakes of methane and ethane. Water is common in the cosmos. But liquid water on a stable, temperate surface, that is rarer. When astronomers detect water vapor in an exoplanet's atmosphere, they become attentive. They analyze temperature profiles. They estimate pressure. They model climate scenarios. Is this vapor part of a gentle hydrological cycle, or the remnant of lost oceans? You sense that water carries memory. If a planet once held oceans that later evaporated, traces of that history may linger in its atmospheric composition. Ratios of hydrogen isotopes can hint at atmospheric escape. The presence or absence of certain gases may suggest past water loss. Atmospheres are archives. You imagine a planet orbiting a red dwarf star. Because red dwarfs are dim, the habitable zone lies close in. The planet may be tidally locked, one side always facing the star, the other in perpetual night. On the day side, water may evaporate continuously. On the night side, it may condense and freeze. Climate models suggest that with a thick enough atmosphere, heat can circulate, preventing extreme contrasts. Clouds may form preferentially on the day side, reflecting light and stabilizing temperature. You see how water vapor, clouds, and atmospheric dynamics intertwine. From afar, scientists simulate these conditions, predicting how spectral signatures would appear under different scenarios. They compare models to observations, searching for consistency. If water vapor is detected alongside moderate temperatures and stable conditions, optimism grows. But water alone does not prove life. You return to that truth gently. Water is necessary for life as you know it, but not sufficient. A planet may be awash in oceans yet remain lifeless. Chemistry requires energy, nutrients, and time. Still, water narrows the search. It transforms a world from sterile rock into potential cradle. You think of Earth again, how oceans regulate climate, absorb carbon dioxide, and support ecosystems. The vast blue expanses seen from space are not decoration, they are active participants in planetary balance. If you could glimpse the reflected light of a distant exoplanet and detect signs of ocean glint, the specular reflection of starlight off liquid surfaces, you would feel a tremor of recognition. But such measurements are extraordinarily difficult. For now, you rely on vapor and clouds. You read faint absorption lines and infer humidity. You observe muted spectra and suspect haze. You piece together clues from incomplete data. The search for life is often indirect. You do not see forests. You do not hear waves. You read the air. And beneath that air, hidden by clouds and distance, there may be oceans remembering their own formation, cycling water through sky and sea. To understand those faint signatures more clearly, you must refine your ability to read light itself. Because every molecule, every cloud, every hint of water reaches you encoded in starlight, waiting to be carefully decoded. Before you can understand distant worlds, you must understand light. Everything you know about exoplanets comes to you in photons, tiny packets of energy that have traveled across space for years, sometimes centuries, before reaching your telescope. Light is not just brightness. It carries structure. It carries memory. When white light passes through a prism, it spreads into a rainbow, red to violet. This spread is a spectrum. Within that spectrum are dark lines, thin and precise, where certain wavelengths are missing. Those lines are not random. Atoms and molecules absorb light at specific energies. Each element, each compound, leaves behind a unique pattern like a barcode written in shadow. You imagine holding that rainbow in your hands. Somewhere within it, oxygen removes a slice of red. Water vapor absorbs in the infrared. Methane, carbon dioxide, sodium, each one subtracts its own precise signature. Astronomers call this spectroscopy. You picture a large space telescope like James Webb Space Telescope unfolding its mirrors in the dark. Its golden surface gathers faint starlight. Instead of simply photographing a planet, it separates the incoming light into its component wavelengths. A spectrograph spreads the light across a detector. Instead of an image, scientists receive a graph, intensity versus wavelength. Where the graph dips, something in the atmosphere has absorbed light. That dip is information. You imagine an exoplanet passing in front of its star, a transit. Most of the starlight shines directly toward you. But a thin portion filters through the planet's atmosphere first. It is that thin atmospheric ring that matters. Within it, gases absorb specific wavelengths. When astronomers compare the star's spectrum during transit to its spectrum when the planet is elsewhere, they subtract one from the other. What remains is the fingerprint of the atmosphere. It feels almost impossible. The signal is tiny, often less than 1% of the total light. Noise from instruments, stellar activity, and cosmic interference must be carefully removed. Yet patterns emerge. You imagine a graph showing gentle troughs in the infrared where water vapor absorbs. Another spectrum reveals sodium, a sharp dip in visible wavelengths. Methane appears as subtle absorption bands. From nothing but variations in brightness across wavelengths, scientists reconstruct atmospheric composition. But interpretation requires caution. Clouds can flatten spectral features, making molecules appear absent when they are merely hidden. Temperature affects how strongly molecules absorb. Pressure broadens spectral lines. Stellar flares can mimic chemical signals. So you do not simply read the spectrum, you model it. Researchers generate thousands of simulated atmospheres with varying temperatures, pressures, and compositions. They calculate what each would look like in transmitted light. Then they compare those models to observed data. It is a process of elimination, of probability. You realize that uncertainty is part of the discipline. When astronomers report the detection of water vapor, they also report confidence levels. They speak of sigma values and statistical significance. they acknowledge margins of error. This humility is strength. You imagine the excitement when a new spectrum arrives. Data from a planet hundreds of light-years away appears as lines of numbers. Scientists process it, calibrate it, correct for instrumental effects. Slowly, the spectrum sharpens. A dip appears at 1.4 micrometers, consistent with water. Another pattern matches carbon dioxide. The combination suggests a thick, warm atmosphere. You are not seeing clouds or oceans directly. You are interpreting absence, the specific absence of certain wavelengths. Light is subtraction. Sometimes, instead of transmission spectroscopy during a transit, astronomers use emission spectroscopy. When a planet passes behind its star, a secondary eclipse, the total light drops slightly. By comparing the combined light before and after the eclipse, scientists isolate the planet's own emitted infrared radiation. That emission spectrum reveals temperature structure. Hotter regions emit more strongly at certain wavelengths. Molecules in the planet's atmosphere imprint absorption or emission features onto its thermal glow. In this way, you measure not only composition but climate. You think about reflected light as well. Some telescopes attempt to directly image exoplanets by blocking out the star's glare. Coronagraphs and starshades reduce starlight so faint planetary light can be studied. Direct imaging allows analysis of reflected spectra, which can reveal clouds, hazes, and surface properties. You begin to appreciate how many techniques converge toward one goal: understanding a world you cannot touch. Each photon is a messenger. It left its star, traveled across space, brushed against a planetary atmosphere, and continued onward. In that brief interaction, molecules altered it slightly, subtracting specific wavelengths. You detect that alteration. The idea feels intimate. A planet hundreds of trillions of kilometers away influences a photon that eventually enters a detector on or near Earth. That tiny interaction becomes knowledge. Spectroscopy is subtle but powerful. It allows you to identify sodium in a hot Jupiter's atmosphere. It reveals carbon dioxide in a temperate world. It detects water vapor in a distant sky. But the deeper goal remains: biosignatures. You recall oxygen, methane, ozone gases that, together, may indicate biological processes. If spectroscopy detects such a combination out of chemical equilibrium, curiosity sharpens. The next chapters will explore the tension more deeply. For now, you focus on the method. You realize that astronomy is not passive stargazing. It is decoding. It is interpretation of faint patterns in light. You imagine future telescopes, larger mirrors, more sensitive detectors capable of resolving even subtler features. With each improvement, your ability to read alien atmospheres sharpens. Perhaps one day you will detect seasonal variations in gas concentrations. Perhaps you will observe changes in cloud cover. Perhaps you will detect the glint of oceans or the faint red edge of vegetation. All of it will come through light. You stand metaphorically beside a spectrograph, watching as a rainbow spreads across a sensor. Within that rainbow, dips and lines quietly describe chemistry, temperature, and motion. You are reading worlds in shadow. And now that you understand how light carries information, you are ready to confront a more profound question. If life alters atmospheres, how would you recognize its signature? The next step is not simply detecting molecules, but discerning imbalance, interaction, and persistence. Because life does not whisper once. It reshapes the air continuously. And somewhere, perhaps already observed in a faint spectrum, that reshaping may be waiting for you to recognize it. You pause in your journey, taking a breath, and remind yourself, not everything is as it seems. In the search for life, the universe can be deceptive. Gases that hint at biology can arise from purely chemical processes. Planets, in their quiet or violent ways, can mimic the signals of living systems. You consider oxygen again. On Earth, oxygen is largely produced by photosynthesis. But elsewhere, oxygen can accumulate through abiotic processes. Ultraviolet light can split water molecules in an atmosphere. Hydrogen escapes into space, leaving oxygen behind. A planet that has lost its oceans might still retain an oxygen-rich atmosphere. To a distant observer, it could appear alive, breathing silently, even though life has never existed there. You think of methane. On Earth, much comes from living organisms, microbes, wetlands, even animal digestion. But methane can also rise from volcanic activity, from chemical reactions deep in the crust. Serpentinization, for instance, occurs when water interacts with certain rocks, generating hydrogen that can combine with carbon to form methane. The universe has ways to create this gas without biology. These false positives are a reminder that signals alone are not proof. You imagine a planet orbiting a volatile star. The star flares unpredictably, bombarding the planet with ultraviolet radiation. That radiation drives chemical reactions in the atmosphere, producing gases like oxygen or ozone without any living processes. From afar, its spectrum might suggest life, but it is only the star's influence shaping chemistry. Planets also evolve. Oceans evaporate. Surface water freezes. Atmospheres thin. Volcanic outgassing continues for eons. Each process changes the chemical balance in ways that can resemble biological activity. Detecting these changes requires context knowledge of stellar type, planetary mass, orbit, temperature, and history. You imagine researchers poring over spectra, considering every potential source of error. Could oxygen result from photodissociation? Could methane arise from geological activity? Are there combinations of gases that are statistically unlikely without biology? Each question demands careful analysis. Life, it seems, leaves a subtle fingerprint, but the universe leaves many footprints that look remarkably similar. You realize the elegance of disequilibrium. Life maintains certain imbalances, sustained over time. But so can planets under the right conditions. The challenge is distinguishing natural chemistry from life's persistent signature. It is a puzzle played across millions of years, viewed from light years away. Even the star itself can deceive. Variable stars, especially young ones, erupt unpredictably. Flares and stellar winds can strip atmospheres, alter chemical compositions, and create transient signals. A planet may appear rich in oxygen one year, then depleted the next. What looked like life may merely be stellar mischief. And yet, you are not discouraged. The discipline required is part of the journey. Patience, repetition, and rigor become your guides. The universe is patient, and science must be as patient as the stars. You reflect on past discoveries. Early claims of life on Mars were later explained by chemical reactions in Martian soil. Initial detections of methane on Mars sparked excitement, then controversy, then moderation. Each false positive teaches a lesson. Caution is necessary, curiosity must be tempered by skepticism. You begin to see a rhythm. Observe. Hypothesize. Model. Test. Reassess. It is slower than imagination would prefer, but far more reliable. In this caution, there is beauty. Science moves like a careful dancer, tracing the line between possibility and certainty. Each measured step builds confidence. Each repeated observation strengthens conviction. You think of the distant exoplanets in the habitable zones of red dwarfs or sun-like stars. Observations of their atmospheres may hint at oxygen, methane, or other molecules. Yet without understanding the planet's context, any claim of life would be premature. The spectrum alone does not tell the whole story. False positives also teach humility. You recognize the vast complexity of planetary systems. Chemistry, physics, geology, and stellar activity intertwine. A planet is not a static stage, it is dynamic, evolving, full of interactions that can trick even the most careful observer. You appreciate that detecting life requires layers of evidence. One molecule, one spectral line, is never enough. Multiple biosignatures, observed over time, strengthen the case. Patterns of disequilibrium, ratios of gases, and corroborating planetary characteristics all contribute to a coherent narrative. You imagine sitting with a team of scientists analyzing data. They discuss models, run simulations, compare results, and debate interpretations. They must account for every alternative explanation. Even a hint of error can lead to false conclusions. The process is slow. It is meticulous. But it is necessary. You realize that the search for life is as much about restraint as it is about discovery. The universe may whisper hints, but it never shouts proof. You listen, analyze, and wait. Still, you cannot ignore the thrill. Each tentative detection carries the possibility that somewhere, life exists. Each spectrum, each dip in light, could point to a world that is breathing, evolving, and enduring. It is a delicate balance between hope and caution. And sometimes, false positives teach you more than certainty ever could. They force you to refine methods, understand nuances, and develop a deeper appreciation for the complexity of planetary systems. They remind you that life is not the only agent capable of shaping a world's chemistry. The universe itself is inventive, creative, and subtle. You imagine a distant world with a rich, oxygenated atmosphere. It might be a false positive water lost, UV-splitting molecules, volcanoes producing methane. But the very possibility that life could exist there excites curiosity and fuels further inquiry. This lesson of patience, skepticism, and careful interpretation becomes central to your understanding. You see that proving life beyond Earth is not about rushing to headlines, it is about building a robust framework capable of withstanding doubt. You let the thoughts settle, even if a signal mimics life, it is still informative. Each false positive illuminates planetary chemistry, atmospheric dynamics, and the influence of stars. They are not failures, they are lessons. And within these lessons, you sense hope. Because when a true signal emerges, when disequilibrium cannot be explained by abiotic processes, when patterns repeat across observations and models converge, it will carry the weight of profound discovery. You feel the anticipation quietly swell, even as you respect the rigor required. You understand that proving life beyond Earth is not a matter of a single spectrum, a single planet, or a single detection. It is the patient accumulation of knowledge, the careful exclusion of false positives, and the synthesis of countless observations. It is science as a slow, rhythmic journey, like waves lapping on a distant, unseen shore. And so you hold this truth gently: the universe can pretend. Planets can whisper false signs. Stars can conspire. But patience, careful study, and repeated observation may one day reveal the undeniable, life's persistent, unmistakable fingerprint in the cosmos. You take one last look at a distant exoplanet's spectral lines and imagine that somewhere beneath its clouds, oceans, or rocky surface, processes unfold that are entirely natural, entirely alive, or some mixture of both. And as you drift from this observation toward contemplation of molecular signatures themselves, you carry forward a quiet question: what patterns, sustained against all natural expectation, would finally convince you that life is real out there? You focus now on a single element: carbon. It is tiny, unassuming, but infinitely versatile. One atom can bond to another in ways that are both predictable and surprising. It can form straight chains, rings, branches, lattices, cages, structures that support complexity and variability. You imagine it as a quiet genius, a master of construction with limitless creativity. Every living cell you carry depends on it. Your DNA, your proteins, your sugars, your fats, all of these molecules are built from carbon. It is the backbone of life, the silent scaffold holding the intricacies of biology together. Yet carbon exists far beyond Earth. You imagine drifting through a dense molecular cloud in the interstellar medium, where dust and gas coalesce under the gentle pull of gravity. In these vast clouds, carbon atoms combine with hydrogen, oxygen, nitrogen, and more, forming organic molecules long before planets take shape. Amino acids, the building blocks of proteins, have been detected in meteorites. Simple sugars, precursors to more complex molecules, drift between stars. The universe, in a sense, scatters its seeds widely. Life's ingredients are not confined to one planet. They float, patiently waiting for the right conditions to awaken. Carbon is the messenger of potential, the promise of chemistry that could give rise to biology. You envision a young planet forming in the disk around a newborn star. Dust and gas swirl, clumping together under gravity. Carbon-rich molecules are incorporated into the surface and oceans, mingling with water, nitrogen, and other volatiles. The stage is set, chemical possibilities assembled. But carbon alone is not enough. It needs energy to drive reactions, water to provide a medium, and stability to allow complex molecules to persist. Life, even in its simplest form, requires a balance, neither chaos nor stagnation. The right energy, at the right time, in the right chemical context, allows molecules to explore, to interact, to form networks that may ultimately reproduce. You imagine watching a primordial soup under alien suns. Carbon chains drift in liquid water. Some break apart. Some recombine. Some form more stable structures. Energy from sunlight or geothermal sources drives reactions. Over countless cycles, complexity grows. Chance and necessity dance together, shaping what may become life. Even on Earth, this process took millions of years. Carbon's versatility allowed it to build structures that could fold, replicate, and catalyze reactions. It became the basis of the first metabolic pathways, the first genetic molecules, the first cell membranes. You feel awe at this quiet genius. Carbon is both simple and profound. One element, for valence electrons, capable of endless forms and combinations. Without it, biology as you know it would not exist. And yet, in the universe, it is abundant, scattered across space, waiting patiently. You imagine a planet far away. It orbits a distant star. Its surface is wet with liquid water, its atmosphere contains carbon dioxide, methane, and traces of other molecules. Perhaps carbon has been incorporated into nascent organic networks. Perhaps, under the right conditions, the first steps toward life have already begun. Carbon's story is intertwined with energy and water. In a temperate environment, energy flows can drive chemical reactions, moving molecules toward more complex arrangements. Water acts as a solvent, allowing molecules to drift, collide, and form new bonds. Temperature fluctuations, mineral surfaces, and environmental gradients provide additional scaffolding for reactions. You recognize that carbon is patient. It waits. It forms and reforms. It bonds, unbonds, and bonds again. Across eons, it allows chemistry to explore possibilities that may eventually culminate in life. The universe's patience is reflected in its chemistry. Even interstellar clouds preserve carbon's potential. In cold, dark regions, simple molecules adhere to dust grains. Ultraviolet light, cosmic rays, and gentle heating drive reactions that gradually build complexity. When these clouds collapse into protostars and protoplanetary disks, carbon-rich compounds are incorporated into planetesimals, comets, and asteroids. Life's building blocks hitch a ride on these small bodies, delivered to young planets through collisions and impacts. You see that carbon is a universal artisan. Its reach extends from interstellar space to oceanic depths, from the earliest chemical reactions to the living cells that now exist. Its versatility creates opportunity wherever conditions permit. You reflect on the pattern. Oxygen, methane, water vapor, these molecules may hint at life in distant atmospheres. But carbon is the foundation upon which such life could arise. Without it, even the most promising chemical disequilibrium would remain barren. You think of the countless exoplanets detected so far. Rocky worlds, ocean worlds, planets in the habitable zone. Many may host carbon in one form or another. The potential is there. Some may develop life, others may not. But the basic ingredients, scattered like seeds across the galaxy, suggest that life's chemistry may be more common than previously imagined. And yet, you understand the fragility of the process. Carbon can form life only when multiple conditions align. Too hot, and molecules break apart. Too cold, and reactions stall. Without water, energy cannot drive reactions effectively. Without stability over time, complexity cannot accumulate. You imagine standing on a distant shoreline, observing a calm ocean under a soft alien sun. Beneath the water, carbon chains drift. Sunlight warms the surface. Energy flows. Molecules interact. Reactions occur quietly. Some structures persist, some vanish. Possibility grows slowly, almost imperceptibly. This image comforts you. Even across the vastness of space and time, chemistry is patient, persistent, and generous. Carbon carries potential across light years. It seeds worlds, sets the stage, and waits for life to take hold. You reflect on yourself, your own body, composed of trillions of carbon-based molecules. You are the product of chemistry's patient artistry. Every breath, every heartbeat, every thought is mediated by carbon's versatility. You are both a witness to and a participant in this intricate chemical story. You lift your gaze to the horizon of human curiosity, where the next generation of instruments waits. The universe has been whispering for eons, and now, humanity prepares to listen more closely than ever. Future telescopes will be larger, sharper, more sensitive, able to capture the faintest photons from planets orbiting distant suns. They will separate light into finer spectral lines, revealing subtleties hidden from today's instruments. You imagine a telescope the size of a city, its mirrors folded delicately into orbit, unfolding like petals under a distant sun. Its sensors are cooled to near absolute zero, minimizing thermal noise, maximizing clarity. It will capture light that has traveled for hundreds of years, photons carrying the history of alien skies. With these tools, astronomers can detect multiple biosignatures simultaneously. Oxygen, methane, water vapor, ozone, carbon dioxide, a symphony of molecules that, together, suggest life. Not a single note, not a solitary whisper, but a chorus sustained across the atmosphere, indicating processes that are persistent, dynamic, and unlikely to arise through geology alone. You picture a distant exoplanet, Earth-sized, orbiting a sun-like star. Its atmosphere is warm and thick. Clouds drift, sometimes hiding oceans, sometimes revealing glimpses of surface features. Light passes through its air, filtered by the molecules it contains. Telescopes measure the starlight during transits. Spectra accumulate over months, years. Slowly, a pattern emerges, a combination of gases out of equilibrium, suggesting chemistry maintained by life. The discovery would not be sudden. It would not appear in a single night. It would be the patient accumulation of data, observations repeated to confirm consistency. Scientists would analyze the ratios of molecules, model the planet's climate, simulate stellar activity, and account for every alternative explanation. The evidence would grow quietly, insistently, like waves shaping a shoreline. You reflect on the journey that brought humanity here. From Galileo peering at Jupiter's moons through a tiny telescope, to the first detection of an exoplanet orbiting a sun-like star in 1995, to today's sophisticated surveys capable of measuring molecules in alien skies. Each step has been gradual, cumulative, and awe-inspiring. You imagine the instruments of the future, space-based observatories with enormous mirrors, free from Earth's turbulent atmosphere, advanced spectrographs capable of resolving absorption features narrower than a single nanometer, coronagraphs and starshades blocking starlight to reveal faint planetary companions. Each technology adds a layer of clarity, precision, and possibility. With these capabilities, we might detect seasonal changes in exoplanet atmospheres, fluctuations in methane or oxygen concentrations, perhaps indicative of biological cycles. Clouds might shift with time, revealing hidden oceans, or hinting at climate patterns. Reflected light could reveal the spectral signature of vegetation, subtle red edges at wavelengths where photosynthetic pigments absorb. The universe may reveal its biosignatures in layers, patiently awaiting recognition. You think of the promise and the patience required. Each observation must be repeated. Each signal scrutinized. False positives are eliminated. Noise is distinguished from meaning. Statistical confidence grows, slowly, methodically. The universe offers hints, and humanity must be careful enough to interpret them correctly. You feel the tension of possibility. Could one of the exoplanets we monitor today already host life? Could a tiny pattern in a spectrum unnoticed so far be the first hint? Perhaps in a few years, more sensitive instruments will clarify what is ambiguous now. Perhaps humanity stands on the brink of a transformative discovery. You imagine the first confirmed detection. A planet with multiple gases in disequilibrium, observed repeatedly, validated across instruments. Oxygen and methane coexist. Water vapor indicates a dynamic hydrological cycle. Perhaps trace gases like nitrous oxide or dimethyl sulfide hint at biological activity. The combined evidence cannot be explained by abiotic processes alone. The announcement would not merely be scientific. It would be cultural, philosophical, existential. Humanity would realize it is not alone. We would see, reflected in a distant sky, that life is not unique to our pale blue dot. Yet, you notice the subtlety. Discovery will not be sudden. It will unfold like a story, layer by layer, observation by observation. Patience and caution will guide interpretation. The cosmos is vast, and certainty requires rigor. You feel a quiet excitement imagining the instruments scanning the skies tonight. Some may already have observed potential biosignatures, buried in data awaiting analysis. Others will come online in the next decade, pushing the limits of sensitivity, resolution, and spectral coverage. The frontier of exoplanetary science is expanding, and you are on the edge of this journey. You also think of the interdisciplinary effort required. Astrophysicists, chemists, planetary scientists, statisticians, and biologists will work together, integrating knowledge to distinguish life from mimicry. Every confirmed signal will represent a triumph of collaboration, patience, and cumulative knowledge. Technology aside, the human element remains essential. Interpretation is an art as well as a science. Understanding context, modeling complex interactions, and weighing probabilities requires intuition informed by evidence. It is both rigorous and imaginative work, marrying data with insight. You picture the next generation of observers, students, young researchers, dreamers learning to read starlight with patience, sensitivity, and humility. Each spectrum is a letter in a cosmic narrative. Each absorption line a punctuation mark in a story that spans millions of years and light-years of space. And within that story lies potential revelation. Perhaps multiple biosignatures will emerge together on a single world. Perhaps patterns repeated across many planets will suggest that life is common, a natural outcome of chemistry under favorable conditions. Perhaps humanity will learn not only that we are not alone, but that life is diverse, adaptive, and resilient in ways we cannot yet imagine. You feel the quiet suspense of anticipation. Discovery is possible, yet it is patient. The universe does not yield its secrets all at once. Each photon, each spectral line, each faint signature of gas must be interpreted, confirmed, and understood. And then, when the moment arrives, when multiple lines of evidence converge, when repeated observations eliminate doubt, a quiet revolution will occur in our understanding of our place in the cosmos. It will be the culmination of centuries of observation, hypothesis, and meticulous analysis. But for now, you wait. You imagine the telescopes sweeping across distant skies, collecting photons, separating light, measuring absorption, refining models, and building confidence slowly, steadily. The universe continues its cycles, planets rotate, atmospheres shift, stars flare and fade, and life or its potential persists in the background, awaiting recognition. You realize that this patient anticipation is part of the wonder. The next generation of signals will not shout, they will whisper, then clarify, then insist upon attention. And when humanity finally understands, the revelation will feel both intimate and cosmic, a connection forged across unimaginable distances. And as you contemplate these future signals, your mind drifts gently toward the molecular signatures themselves, the ultimate indicators of life, and you wonder what a distant planet might look like if those signals were confirmed. You gaze upward, letting your thoughts drift across the night sky. The stars seem closer now, not because they have moved, but because your mind has expanded to include the hidden worlds that orbit them. Each pinprick of light may harbor a planet, an atmosphere, perhaps even the subtle stirrings of life. You imagine a distant world where oxygen and methane coexist in delicate imbalance. The chemicals shimmer invisibly in the air, unseen yet detectable. Their persistence is a quiet testament to processes that cannot be explained by geology alone. Somewhere, perhaps, life is maintaining that balance, just as photosynthesis and microbial metabolism sustain the atmosphere of your own planet. It is humbling. The idea that biology could exist elsewhere reminds you that life is not confined to one story, one place, or one set of conditions. Across the galaxy, under alien suns, carbon chains may twist into complex molecules. Water may ripple in oceans, clouds drift lazily across skies, and gases may dance together in quiet rhythms. You feel a kinship with these distant worlds. Though separated by unimaginable distances, they share the same fundamental elements, the same chemistry that built your body, your thoughts, your imagination. Carbon, hydrogen, oxygen, nitrogen, the same atoms that compose you also form the scaffolding of potential life far away. And yet, uncertainty remains. Perhaps the signals you imagine are false positives, chemistry pretending to be life. Perhaps some distant atmosphere pulses with oxygen only because hydrogen escaped, or methane rises from deep geological reactions. The universe is patient and subtle. Proof requires time, observation, and caution. But you cannot ignore possibility. Each faint spectrum, each carefully measured absorption line, carries the potential to reveal a truth that would reshape your perspective. Life, if detected elsewhere, would no longer be an abstraction. It would be a shared experience, a cosmic truth reflected across the light years. You think of the first generations of telescopes and instruments. They peered at distant suns, measured tiny dips in starlight, and built a foundation for the observations of today. Each step, from the detection of a single exoplanet to the measurement of its atmosphere, has brought you closer to hearing the molecules speak. Now, as technology advances, you imagine the future, telescopes capable of analyzing hundreds of planets simultaneously, instruments that can detect subtle seasonal variations in atmospheric composition, and spectrographs so sensitive that even thin hazes cannot hide the chemical fingerprints of potential life. You let your imagination drift across those alien skies. Perhaps a planet orbits a red dwarf, tidally locked so one side basks eternally in light while the other sleeps in darkness. Clouds swirl over its hot side, carrying water vapor into the atmosphere. Methane drifts, oxygen glimmers faintly in balance. The molecules communicate their presence quietly, a subtle message waiting for you to understand. The knowledge that life is not confined to Earth could reshape philosophy, culture, and perspective. Isolation gives way to connection. The night sky no longer feels distant, it feels shared. Each star might host a story, each planet a narrative unfolding in silence yet detectable to those who listen carefully. And yet, the molecules do not shout. They whisper. Their signals are subtle, embedded in spectra, hidden in absorption lines, nuanced by clouds, temperature, and atmospheric dynamics. Detecting them requires patience, precision, and humility. You imagine scientists, careful and persistent, tracing these whispers, decoding the chemistry of atmospheres, constructing a coherent story from faint, scattered clues. The molecules that may indicate life elsewhere mirror the molecules within yourself. You are connected to the cosmos in ways both chemical and philosophical, a participant in a shared story spanning billions of years and countless light years of distance. And in this reflection, sleep begins to approach. Your mind relaxes into the rhythm of imagined exoplanetary skies. Clouds swirl, oceans ripple, quiet communion with the universe. And as you drift deeper into sleep, one final question lingers, gentle but persistent: if life is common among the stars, if molecules can sustain complexity elsewhere, what does that make you? You let the thought settle. The night sky holds countless worlds, each with potential, each with chemistry humming quietly. The molecules speak, and though their words are subtle, their message resonates. The universe is alive in possibility, and in listening, you are part of that resonance. And with that thought, your mind softens, the stars blur into dream, and you drift into a sleep that is itself part of the endless, patient rhythm of the cosmos.